Okay. Okay. So, well, testing in linear regression, we have this same model as always. We want to test basically one entry in this vector beta, which we call beta s. By conditioning on everything else in that beta parameter, said that, well, we do that by setting up a null hypothesis which says that the true underlying beta is 0, which means that this variable doesn't have an influence on the phenotype or on the variable y here. And as a test statistic, we'll use the estimate, the maximum likelihood estimate. And the intuition is that the larger this estimate, the less likely is the hypothesis that this is 0. Well, I said what we mean by hypothesis testing. Well, basically, in order to test a hypothesis, we have to define a null hypothesis. In this case, this beta value is 0, and an alternative hypothesis, which can have basically every value except for 0. And in order to show that the alternative is true, you have to perform a statistical test rejecting the null hypothesis. And if we do some tests, then there's something that we call a type 1 error, which means that the null hypothesis is true. So there is in the association testing setting no association, but we call it significant. So we reject the null, or a type 2 error. The null hypothesis is accepted, but does not hold, which means that we basically miss a test that would be significant. And well, in order to do such a testing, we also need a significance level alpha, and we said basically the significance level alpha can be is basically a region defines a region in the probability distribution over the test statistic under the null distribution, where we say, okay, if we observe a test statistic in that region, which we call it critical region, then the test is significant. So it's basically a region that has values of the test statistics that are very unlikely under the null, such that we say, okay, we accept that the null is quite unlikely. So say if that is 1% of the total probability mass under this function, then it's unlikely enough. So that would correspond to a significance level alpha equals 1%. And there are tests that are one-sided, where we say, okay, we only look at, for example, values that are larger than a certain threshold, or two-sided tests, like in the Gaussian case, that is symmetric. If we just want to see that something deviates from 0, then it can be large enough or small enough. In this case, basically we put half of the mass on either side of the distribution for symmetry. Well, and the p-value of a test statistic is the largest possible alpha, so the largest possible significance threshold, such that the hypothesis would still be rejected, which basically means that the probability of observing a test statistic is at least extreme as x is given by the p-value. So you can interpret basically the p-value as a probability of the null hypothesis being accepted. Or of observing a test statistic under the null that is at least as extreme. And now alpha trivially becomes the threshold on the p-value. Okay, so the problem is, in order to define a p-value, you need to know the distribution of test statistics. That's something that we don't always have. And if we have it, then basically the p-value is uniformly distributed. And this uniformly distributed property is what we, in the end, for example, used for FDR control. That's something that we need for that. Well, if we don't know it, there are ways to obtain this null distribution, for example, by doing permutations, where we basically say, well, we have our regression model, we have those are the covariates that we want to condition on, this is the variable that we want to test. Now, if we permute these two and leave these the same, or keep these the same and permute these, it turns out to be the same, and compute our test statistics again, then we break any dependence between this and the other two groups, and for that reason we should get an empirical null distribution. And now we can use, if we get enough of these, we get basically kind of a histogram that has a fine enough resolution that we can estimate probabilities of observing a real test statistic under the null distribution. And the p-value is then the quantile of real test statistics in the artificial null distribution. Well, we also said, given our results on the Gaussian distribution, we can write down an analytic version for the distribution of this regression coefficient, where we basically say that the regression coefficient is basically just a linear transformation of something that is Gaussian distributed under the null distribution. So y under the null distribution follows this Gaussian distribution, where just this one beta s that we want to test is 0. And for that reason, because it's just a linear transformation of a Gaussian distribution, we can also write it as a Gaussian distributed variable, where we have the linear transformation of the mean here, and well, a kind of two-sided transformation of the covariance matrix. And well, canceling out everything that we don't need, we get this distribution here, which is basically, it has a mean at the true beta, the unknown beta under the null distribution, and a covariance matrix equals to the inverse of the inner product of the design matrix. Well, because we are only interested in one entry of the betas, we can also just write down the distribution of that one beta, and that we do by using marginalization. We said in a multivariate Gaussian distribution, we can marginalize if we only look at that one entry of the mean, which is 0, because it's beta s, and the corresponding block of the covariance matrix, which in this case is one diagonal element. So it's basically the s element of the diagonal of this x transpose x inverse times the variance. So now we kind of have an idea what the distribution is, and we can, just because it's a Gaussian distribution, we can basically compute the p-value as from the cumulative distribution function. And now, because it's a two-sided test, the p-value is now 2 times the minimum of, well, the CDF of beta, which is for the case where beta is small, or 1 minus the CDF of beta for the case where this cumulative distribution is very large. And the 2 accounts for this two-sidedness. Well, there is a glitch, right? And the glitch is that there's one variable in this Gaussian distribution which is typically unknown, and that's the variance. And so this is a nuisance parameter. Usually we want to get rid of nuisance parameters. We already managed to get rid of all the other nuisance parameters in the model, which were the other beta variables. We got rid of them by marginalizing them out, so they didn't appear anymore. But this one we cannot get rid of. Well, we can get rid of, but it's too complicated to write down. But I just say that the result, and it's basically we can compute the sample estimate, corrected, so the unbiased sample estimate corrected for the degrees of freedom in beta d, and plug that in instead of this this standard standard deviation here. Oh yeah, this is a square, not a, still a square, not a sub 2 here. And it turns out, well, there's basically you can show that this is a chi-squared distributed variable, which is independent of this Gaussian distributed variable that we are dividing by it. And if you have this Gaussian distributed variable divided by a chi-squared distributed variable that is independent, you get a t-distributed variable.
Quick question: is sigma squared, does that correspond to like the variance due to the environment in GLOS?
It's everything. Yeah, it's basically the environmental variance. It's everything that is not attributed to the covariates or the SNP that you're testing. Yeah. Which means that if you didn't include some other covariates in the model, then they are also kind of treated as noise. Yeah. Right. And so we can basically. We need to do this whenever we have small sample sizes. If we have large sample sizes, just plugging in the Gaussian distribution is fine. If you have small sample sizes, then actually this matters. And basically what happens if you go from a Gaussian to a chi-squared distribution is that the tails are heavier. And well, why do we need these heavy tails? It basically means that, well, we're estimating one nuisance parameter in this model, right? And whenever that estimate is good, then we're kind of in the region where also the Gaussian would lie. But if that estimate is bad, then we're dividing basically something that is Gaussian by something that is off, basically in order to get something that we would hope is kind of a standard normal, right? I mean, we're basically trying to get this variable which is standard normal, and we're plugging something in that we don't know. If this is off, then we are going very far away from the actual standard normal. And for that reason, we need to be kind of robust in the tails and also give some probability. Basically, there is a probability that we get values that are far off the mean of the standard normal just by chance because we get a bad estimate in this variance parameter here. That is kind of why we need a heavy-tailed distribution. So heavy-tailed distributions are in general more robust than non-heavy-tailed distributions. Well, we basically said there are some basically simple ways to calculate, like go from one distributed variable to another, and there are some rules that people have worked out. The typical way that people work it out is by looking at functions that are kind of unique for a given probability distribution, and for example, the moment generating function, and then or the CDF or so, and then map one of these to the other by doing a change of variables. But we don't have to care about them. We can just look it up for some of them. For example, if we take the sum of squares of standard normals, we get something that is a chi-squared with n degrees of freedom. This is what we used before. If you have the ratio of a standard normal and an independent chi-squared with n degrees of freedom, and then some, which is divided by n, in this case by the number of degrees of freedom, then we have a student t with n degrees of freedom. And so basically the way to get from the normal to the student t result is by proving that this estimate of the variance is a chi-squared with n minus d degrees of freedom, where d is the number of parameters in beta, and that it's independent of the beta. That's how the proof goes, and it's possible to do that. And if you have, well, the ratio between two chi-squared distributed variables that are independent of each other, then we have got an F distribution. And for example, there's a way to get from here to the F distribution, for example, just by squaring the t. If you take a t-distributed variable, you square it, you have the squared of a standard normal, which is a chi-squared with 1 degree of freedom. and you have the square of a square root of a chi-squared, which is also a chi-squared. This is independent of this, so you have the ratio of two chi-squares that are independent of each other. Okay, so another test is the likelihood ratio test, and the idea here is basically to write down the likelihood under the null model and under the alternative model, and say, well, if this ratio is large enough, so if introducing this extra parameter, letting it move freely and estimated by maximum likelihood, if that helps enough, then we call the test also significant. Actually, if you want to get a p-value out of that, you usually go to the log likelihood ratio. So you take the log of that ratio, which makes it a difference of the log probabilities. And well, Wilk's theorem basically shows that for very large sample sizes, or for large sample sizes, 2 times the log likelihood ratio follows a chi-square distribution with 1 degrees of freedom, where the degrees of freedom are given basically by the difference of the number of parameters between these two models, which is 1 in this case. Because only one only one of the values is fixed that can move freely here and is estimated by maximum likelihood. And so we get the p-value by 1 minus the CDF of chi-squared. This time it's only a one-sided test because this is always positive. So it's always, if it's larger than a certain threshold, then we call it significant. Okay. Well, we also talked about multiple hypothesis testing, and the idea is basically if we perform many tests, then because the significance level alpha can be is equal to the probability of making a false discovery or a type 1 error. If we just test often enough, we'll make a lot of these. If, for example, we say we have an alpha of 1%. And so the probability, if we test often enough, of making 0 false discoveries, 0 type 1 errors, pretty quickly goes to 0, or the probability of making at least 1, which is 1 minus that, goes to 1. So this means we kind of have to account for that, because if you test often enough with a standard p-value threshold, then this is pretty meaningless in practice. And what people do most is controlling the family-wise error rate instead of the standard error rate. The family-wise error rate is the probability of making at least one type 1 error, sorry, in all the tests. And instead of bounding basically the type 1 error per test, we now bound this. And Bonferroni correction does it by just comparing the p-value. Instead of comparing it to alpha, we compare it by alpha divided by the number of tests. And the reason why this works is because it builds on Boole's inequality, where it basically says the probability of jointly observing at least one p-value that is smaller than alpha is smaller than the sum of all the probabilities, because sometimes they overlap, so this is an inequality that holds. And now basically the sum of probabilities, so because all of these probabilities are alpha, you basically have to, the sum here just is alpha times the number of tests where the null hypothesis is true, right? So this is alpha times S0, where S0 is the number of null hypotheses in our data set. And, well, this is obviously smaller or equal than the number of total hypotheses that we're testing. Okay? Well, the problem is that this, in practical settings, this is often very conservative. So basically going from a significance level of on each test to a significance level that says, like, in my 1 million individual tests, I don't want a single mistake. That is pretty drastic. And what people do in order to make it less drastic is, for example, come up with something like the family bias, with something like the false discovery rate, where we say, okay, because we do so many tests, as long as we get some positive results, I'm willing to also accept some negative results as long as the rate between these two is large enough. So basically, if the expected number of false discoveries, false positives over the total positives that I get is small enough. This is the so-called false discovery rate. And well, it's pretty trivial. If there are no false positives in the data set, if there are no true positives in the data set, so there are no cases where the null hypothesis actually doesn't hold, then this cannot be bounded. But this is a rather uninteresting case, but just to note that. And the question is now, how do we, I mean, this is now kind of an awkward concept. We're given p-values, and the question is, how can we control this false discovery rate? And this is kind of where I think we all struggled a bit last week. This idea how we basically can fit a linear function, can say basically a linear function gives us the expected false discovery rate, whereas the linear function of the rank of the sorted p-values. And well, if you think about it, so say I plot a histogram of my p-values that are all now null hypotheses. So between 0 and 1, that's my p-values. My histogram should look like that, right? And because I said the p-value is uniformly distributed, so this should be my histogram over the null p-values. Now, say for my alternatives, I mean, if I'm smart enough and don't, write down a test where I also get a uniform distribution, but something where actually under the alternative I get a small p-value, and I'll probably get some distribution that looks like that. Those are the alternatives. So this is H1, this is H0. Now what I really observe is the sum of the two, right? So I observe something like that. If I took now only those and well, sorted my p-values and plotted basically the p-values versus the rank for only the null hypothesis, I would get just a straight line, right? On average, as an expectation. And so this is the rank of the sorted p-value, and this is the p-value. But if I also plot these, then I get something that looks like that. And, yeah, it's something like that. Because I basically shift, I take this line, it should be parallel. I basically take this line and shift it to the right, assuming these here are only a few. So I know that among these here, I can now estimate how many false discoveries are here. And that's basically just these here, right? These are the false discoveries that I would expect in this region where I'm not, I don't have this straight line. So, and I know how many discoveries I have here, and that is basically the rank, right? That's the number of discoveries that I have. That's the number of p-values that are smaller than this one. And basically by taking this estimate of the number of false discoveries and, well, my observed number of discoveries, I can get an estimate of the false discovery rate at this threshold. That's the idea behind the false discovery rate control.
Question.
Yeah.
So you're trying to pick the right p-value to keep your false discovery rate at a certain level?
Yes. I'm trying to find the cutoff on the p-values. So I say I want to find a threshold such that my false discovery rate is smaller than 10%, 5%, whatever, right? Then I cannot just say, okay, yeah, that's a p-value threshold of 5%. No. It's actually a p-value cutoff of, that can be completely arbitrary. And but I can now get an estimate of this p-value cutoff by comparing basically the known p-value distribution under the null, which is a uniform, to something that is non-uniform, and hopefully smaller, has many small p-values. Of course, I can also design a test that gives you very many large p-values under the null, which is a pretty stupid test. But yeah. So that's the idea here. And well, an estimate of the false discovery rate at a given I, so at a given rank, is basically the expectation of the false positives. That is not clear what this is, over well, the number of false positives plus false negatives if we chose the p-value of the ith statistic as a cutoff. Right? That's just I, because if it's the p-value of the ith p-value, we have I significant p-values at that position. So we know that part of the false discovery rate. The question is, how can we get the expectation of that? Well, as I said, because of this uniformity, basically this should be the number of total false true null hypotheses, which is S0, times the current p-value. Right? That's exactly this part here. Because it's supposed to be a linear function under the null. So that is why we can get an estimate for the number of false positives. And of course I can now upper bound that here by the number of total tests instead of, because S0 is not known, we only know S. This is an upper bound for that.
Maybe true positive instead of false negative.
False positives plus. Yes, right. Yeah, correct. Yes. Okay, so this is basically what this procedure does. It computes basically this false discovery rate for every threshold, which also means that because we want a cutoff on the false discovery rate, basically we can use alpha now over this estimate. Basically the estimate of the false discovery rate is S over I times, well, S over I times P. So if we want S over I times P to be smaller or equal to alpha, we just bring S over I to the other side by dividing by it. So it's I over S times alpha. So it's just, we want this here, S over I times P to be smaller than alpha. So we multiply by I, so we have I times alpha, we divide by S. So we have P has to be smaller than I over S times alpha. Okay. And then, and something quite interesting is that if we actually increase I, if the p-value does not increase linearly in I, actually our estimate of the false discovery rate would go down. So by giving you a higher cutoff, I can actually achieve a lower false discovery rate. So that is the really counterintuitive thing about the false discovery rate. So the false discovery rate at the cutoff depends on our observed p-values. And for example, if, say, I have a weird distribution where I observe some small ones and then so say my alternative looks like that, right? I mean, I have something, it's like that. Then in the beginning, I will, basically, the p-value distribution will look like that, and the this thing would look linear in the beginning because we are having mostly nulls here. Then probably it would stay small and then go linear again. And in this region, we would actually reduce the false discovery rate by accepting more p-values. Okay. Yeah, and this is just, here it's also a true negative, so that's correct here. Okay, so I hope this sheds some more light into the false discovery rate control. And the definition of a Q value is basically the minimum false discovery rate that I could achieve while calling that feature still significant, which is not the false discovery rate when setting the threshold like that. But because the false discovery rate can go down when calling more significant, it's actually the smallest at p-values larger or equal to the current p-value. And well, if we compute the false discovery rate at every single hypothesis using the procedure, using the algorithm I just described, we can just read off by now going from right to left. We can just read off the Q values. Okay, so this was where we stopped last week. Yeah.
The quick question was the Benjamini procedure. So if you just plot all the p-values you have, for example, I'm assuming you're using real data. Like, is it practical to just choose some threshold just based on looking at it, or I mean some like false discovery rate alpha? Is it practical to just choose an alpha just by hand, just by looking at your distribution, or are there some better like processes?
I mean, in theory, you can basically think of, well, you can attach basically a cost to each false positive that you get, and but kind of a benefit from each true positive that you get, right? Or I mean, there's probably some follow-up cost if you report something, because a biologist might have to go to the lab and actually like look at it, do a knockout with that or whatever, right? I mean, so there's a cost. But if it's true, so if it's a true report, then you probably can write a publication about it or find some treatment and earn some money, I don't know, cure a disease. So you can basically kind of attach costs and benefits. And if you then do the math, then you say, okay, I probably have a certain budget of the total number of things that I can look at all. And well, as long as I stay below that budget, I basically want, basically based on my costs, the false discovery rate to be smaller than something. I mean, that's not something that people do in practice, but that's something that like theory would enable you to do. Okay, so another question is, okay, now I get all my tested p-values back, and now say it's 1 million p-values, and the question is now, well, I kind of put a lot of assumptions in this because I put the assumption that I have the true null distribution. Well, under the null distribution, we know that the p-values should be uniformly distributed. I kind of say I have kind of an estimate that probably there are not too many positives in the data. And I can kind of think of how my p-value distribution should look like in theory. So if I say there are probably most of my tests, so 99% of my tests are actually true nulls, then I know that, well, it should be basically uniform except for 1% that don't follow the uniform distribution. So I kind of can take the empirical distribution, in this case I can take the empirical distribution of my p-values kind of as a sanity check. In order to check whether I use the right null model. I think I said all of these. So that's kind of one thing that is where the large number of tests we're currently doing is very useful. And if basically I have now a p-value distribution that completely doesn't match my intuition or my prior knowledge, then well, I have to basically change my model, change my test. That's something that is useful in practice. And well, I mean, we basically said we can do plot just a histogram, but what we're usually interested in is more the tail of the distribution, and so it makes more sense to look at the p-values on a log scale. And if we want to look at the log scale, we basically can use the so-called quantile-quantile plot. Well, we sort this test statistics, and we plot the test statistics on the y-axis, basically the sorted ones, against the theoretical quantiles of the null distribution. We know that the null p-values are uniform, so say we take log minus log 10 p-values, then we can just take minus log 10 of uniformly distributed values on the grid between 0 and 1, take the log of those, and plot them against what we observed. And well, in theory, we should, if everything comes from the null, then we should get something that follows the diagonal. Well, in this case, we can say, yeah, I mean, this kind of matches the null hypothesis. In theory, basically, we would assume that a lot of these things are on the diagonal, and then in the end, you kind of get some that deviate from the diagonal because of this, because of the alternatives that are mixed in. And well, if I have something that completely doesn't match the diagonal, then I can, for example, say also my null distribution doesn't hold, right? Is this clear? So the expected log p-values are just say I have 1 million p-values. I just place uniformly, like my expected quantiles are just uniformly between 0 and 1 million of them. So I just basically go from 0 to 1 in steps of 1 over 1 million. Those are my my kind of expected p-values. I take the log of those, and I plot the negative log of those versus the negative log of my observed p-values, then I should get either something on the diagonal or something that deviates from the diagonal. It can also go the other way. If it goes the other way, it means that my p-values are mostly close to 1. Then I'm basically too conservative. That even if everything is under the null, I wouldn't call anything significant. Yeah, even more so then. And well, basically there's one idea is now, okay, so say I want to stay with those p-values. Now I can just say, okay, I can match some quantiles of this distribution. So for example, if I assume that most of my p-values come from the null, I can say, for example, if the median, so the 50% quantile, should probably be a null p-value. So this is kind of what the so-called genomic control procedure does. It computes the ratio of the 50% quantile under the null, which is minus log of 0.5 over the minus log of the observed. And under this assumption that basically the 50th percent quantile should still be a null, then this should be close to 1. And if it's much larger than 1, like for example here we have a 1.4, then I have something that I would call inflation. And if it's much smaller than 1, I would call it deflation. And if I now want to basically say, okay, I want to control for this, I want my quantiles to match up, I can just say, okay, I just divide all my test statistics by this, so all my log 10 p-values, for example, by this ratio. And then by definition, you will get a lambda of 1 after that. So the problem with this is really conservative, typically. And it also makes a really strong assumption. I mean, it matches one quantile. You can also, for example, match several quantiles. You don't have to do it with one single quantile. It doesn't have to be the 50th percent quantile. It's kind of all assumptions. I mean, typically people do it with the 50th percent quantile, but it could also be the 75th percent quantile or the 90th percent quantile. But one has to be basically be aware that this is a strong assumption here. Basically, it's the assumption that the 50th percent quantile of the p-values is null. And sometimes it's not clear whether this actually holds in practice. I mean, it doesn't hold, then you're losing power by doing this. You're basically sacrificing a lot of power in order to control type 1 error. And one in GWAS, currently there's many assumptions where actually this is the case. If you have, for example, if you have a phenotype like human height that is controlled by thousands of individual mutations, if you test all of them, because then you basically you don't just observe a few thousand of very small p-values, but you also have, because of because neighboring markers, neighboring SNPs are correlated, you will basically get very broad inflation, so very many small p-values. You will get very many associations, and for that reason, for example, lambdas might just actually not be 1. And with the very large sample sizes that people have today in GWAS, where people do genome-wide association studies on 1 million people or so, there's actually the power of these genome-wide association studies is so large that if just these tiny bits of correlations between the causal SNPs and the neighboring SNPs might drive lambda in 2-3 or so, 2-3 or so, and it's completely just explainable by the number of causal SNPs in these phenotypes. So one always has to be a little bit.
Do you think that's a good that study? Because that study seems like a sort of bad idea, given it seems too general a thing to measure from SNPs, because you would assume that measuring femur length or something might be a better study, just because the number of SNPs that controls human height, it's your skull and your feet and all the bones in your body.
Yes, I mean that's also the reason why there's probably a lot of stuff involved, right?
Yeah.
I'm not saying that it's the ultimately most sensible thing to do to look for. I don't know. I mean, there are many SNPs that, because they, for example, make your skull a little bit, I don't know, distort your skull a little bit, right? I mean, they make you like a couple of millimeters taller, right? I mean, is that interesting? I don't know. I mean, it's certainly something that is being studied a lot. Yeah.
Yeah. Like while there are a lot of variants that account for height, like whenever any GWAS is taken, they always like say what height is the person, so someone can take all of that data and do a meta study. And so even if one SNP accounts for very, very, very small portions, like the beta values are like minuscule, you can still detect them significantly because you're looking at like 5 million individuals, if not more. So.
Yeah, I mean it's so okay. I mean, the point is looking at height is a pretty easy thing to do. So you can measure height for a lot of people. It's not so easy to get for several million people measure of their, I don't know, like the length of a finger or whatever, right? I mean, it's or of some processes that go on in the cell that influence the height in the end, right? So there are a lot of these phenotypes where basically the phenotypes just come for free. Height is one example. And I mean, genotyping is getting almost for free now. I mean, it's like measuring 1 million or 2 million within an Illumina chip. That's a couple of bucks now. So it's really easy to do these studies. And of course, it's kind of interesting to look at just mostly to quantify what is in there. I mean, this is not about really. I mean, it won't give you many biological insights in the sense that you find a mutation that causes some process that in the end makes you taller or smaller, right? I mean, just kind of, it's a quantification what's in there. Once we have kind of found everything using other things that explains all the height, then we know we can stop. But it's kind of like just sets kind of an upper bound on what is there, what can be found. Okay, so now the next part is linear regression. Do you want to do a pause, or should we just keep on? Are you awake?
Take a short pause.
Okay, let's take a short pause. Okay, so well, we already talked about linear regression before, and so far we only looked at it mostly for I mean, we used it so far only for statistical testing, but we'll now look more at predictions and about how to compare alternative models. And then we'll talk about Bayesian and regularized regression. So those are ways for basically accounting for the fact that, well, there's some uncertainty in the regression function. I mean, say this is the true regression function that generated the data if you want to estimate it. I mean, there are a lot of regression functions that give you a very similar fit. And another thing that we'll cover, and that is especially very nice because it gives us a simple way to, in a two-dimensional plot, give us more than a boring straight line, is by looking at generalized basis functions, where basically we can, given a single input variable, we can still get a nonlinear function. So, I mean, this course is, I mean, this lecture is like very close to the Bishop book, chapter 1 and chapter 3. And well, for the Bayesian part, like there are some, like all the Gaussian calculations are always useful. For example, in this, I think there are some better ones than some robots. So I can send you around some stuff, put something online. Okay. Well, we are where we were before. We have a data set We have some parameters of a function plus some noise, so the parameters, and basically we say, well, if this noise is Gaussian distributed, then if we have this function, it basically means that we have a Gaussian distribution where the mean of y is equal to this function. And the variance of y is equal to the variance of this independent noise. Now, in a linear regression, well, this function is linear. So basically we have just some input variable x, and we multiply it by the parameter vector beta. Which also, again, includes the bias. It's this graphical model. We said how to obtain the maximum likelihood estimate. It's basically, we saw that the likelihood is maximized when the squared error is minimized. So, and the squared error is due to this Gaussian distribution. Because if you take the log of a Gaussian, then we have basically then the noise basically explains a kind of a squared difference between the variance in the noise explains the squared difference between the mean of the phenotype, which is the linear function, and the phenotype. So these squares in maximum likelihood are equivalent. So it gives us a linear function with squared difference, minimum squared difference to all our samples. Well, we said how to get the maximum likelihood estimate by taking the pseudo-inverse of our x's, multiplying it to y. That's the maximum likelihood estimate for the regression weights. That was maximum likelihood estimation, and now the next bit is how do we get nonlinear relationships. So, I mean, well, say we want have a single x, but the dependence between x and y is not a straight line, but for example the y goes up and then goes down again. We wouldn't be able to do that with a linear function, because the linear function would probably go like that or would go like that. I don't know. It would probably not fit this model very well. How can we obtain a new x or a couple of new x's such that if we fit a linear function to these new x's, we can learn this nonlinear function. Or something that I cannot plot is instead of, well, if I have many x's, so if I have, for example, many SNPs that control a phenotype, then we'll talk also on how to use many SNPs and fit a linear function to those, or also possible nonlinear function. Okay, so the simplest possible nonlinear function that you can think of is just you take your x and you take a polynomial. Just take powers, so x to the 0, x to the 1, x to the 2, x to k, where k is the degree of your polynomial. And you fit, for each of those, you fit a different regression weight. So these are different polynomials. So you have your 0th order polynomial, which is just basically that will be your bias term, right? So then you have a 1st order polynomial, 2nd order polynomial, and so on, right? And now instead of using in the regression our original x's, we use phi of x's, where basically we define phi of x as the vector of these powers of x. But in principle, we're not just restricted to polynomials. We can use whatever function that is interesting. It's also, again, prior knowledge. If you think your data can be described well by a polynomial, use a polynomial. If there's something else going on, use something else, for example. You might observe that kind of your y's correspond kind of to a power of in x or so. I mean, so you might want, for example, a log, or you might want an exponential function, or both. I mean, say you have a linear component and a logarithmic component, then you might basically might choose one phi, which is just x itself. The other one might be a logarithm or so. Other very typical basis functions that are being used a lot are just little Gaussians. So for example, say you place on the real line, on your x line, many Gaussians, right? Different means, and possibly different variants, or maybe the same variants. Then you can now define a basis function which kind of corresponds to the density that your x achieves under this Gaussian. So, say you were using this violet one here, which has a mean at here. So just mu j would be probably like minus 0.3 or so. We take our x, which might lie here, compute the density under that would be 0. Okay, we go to the next one, get a higher density, and this gives us several phi of x's to work with. And this is what is either called RBF, radial basis functions, or Gaussian basis functions. And these Gaussian basis functions, they have basically two parameters. One is a mean, the other one is kind of corresponds to the variance of these. So if the variance is larger, then if our x is further away from the mean, it would still basically get a positive value there. Or we might use some sigmoidal basis functions. That is, for example, done a lot in neural networks. They basically kind of do a regression using sigmoidal basis functions in your data, where the sigmoid basically, you again place the you place the sigmoid at some point in the x, so that corresponds to the mu, and then you measure the distance between this corresponding mean of the sigmoid kind of and your x, again divided by some scale, and plug that whole thing then into one of those sigmoids, and then you use you map from your x to the different sigmoids. For example, to this you get an 0.1 back, to this you get an 0.25 back, here you get an 0.7 back, and here you get a 1 back. So you get 4 different non-zero features to work with. Is this idea clear? How we get from a single x, or we're not just, for example, with polynomials, we are not just restricted to single x's. We can think of you've got 2 inputs, and you can also combine the 2 in a polynomial. Say you choose x1 times x2, or x1 times the square of x2, or something like that, as a polynomial, as a basis function. And for example, if you want in a GWAS to look at epistasis between 2 SNPs, then you might want a product of 2 SNPs. Or if you want to look at epistasis is one fact. Basically, whenever you want to look at nonlinear relationships between variables, then you have to use something like that. All right, so this is now basically, but once we have those basis functions, we can basically do the same thing as we did in the linear regression. We just replace our original x by this phi of x. You can again write a matrix which we call phi, which is just for each sample all the evaluated basis functions for the x value, right? And say we use polynomials, and we fit now a polynomial, for example. So we have this artificial data set where we have 4, 5, 6, 7, 8, 9, 10 observations, right? We have the true function is a sigmoid plus Gaussian noise, and now we fit a polynomial to that. For example, if you start with a 0th order polynomial, you might get this fit. So it's just a straight line. Fit the first order polynomial, which corresponds to the linear regression. We get this line here. Well, we go to a third order polynomial, which is now x to the 0 plus beta 1 times x to the 0, beta 2 times x to the 1, up to beta 3 to x to the squared. And no, to the third, we get a line that already quite well fits the true sigmoid. So this is a way to fit these nonlinear functions. Now we can again, I mean, this is all using maximum likelihood estimation. So it uses exactly the same formulas as before, just replacing the x by this phi of x. And if we go to a ninth order polynomial, we get something like that. And if we compare these two functions, this tracks the original function quite well. If we look at this function, we also see that we can get some really unrealistic functions back. I mean, gets a perfect fit of our 10 data samples, but well, if we say we get a new x here and we want to get its y value, then well, we would probably predict the y value to be very like probably -3 or so. So the number of these basis functions that we use kind of regulates the complexity of our model. If we use many of them, the model might get very complex and might overfit. If we choose too few, we get something that probably doesn't explain the data very well because it underfits. So it's kind of getting this right. Yeah.
So of course you can introduce some sort of penalty terms for, you know, if you want to automate this process, for example, you can always introduce some penalty terms like for the order of the polynomial or whatever. But is there a way to choose a polynomial that would, I guess, most realistically describe the noise around it? I mean, because we know that the noise is, for example, if we assume that it's Gaussian distributed, then is there a way to just look at the points around the fit and see which one of them would be most realistic? Because of course the ninth order polynomial is very unlikely for all of them to be exactly.
Well, yeah, I mean, but this depends on the variance of that noise. If you know the variance of that noise, you can basically kind of get an estimate of what the squared error should be like that you should get, right? Mm-hmm. But if you don't know that variance, I mean, you only observe these 10 points. I mean, the best thing that you can do, fit it completely, right? I mean, it's not the best thing, but it's like that's what the maximum likelihood estimate would do for you.
I think one standard way is to do cross-validation.
Yes, I mean, we'll talk about that.
Okay.
Yeah. Okay, so that's one thing, kind of the number of these functions or the number of features. I mean, doesn't have to be a ninth order polynomial if we just use many, for example, different x's, for example, different SNPs or so. We also will get a function that fits the phenotype very well. So if we use 1,000,000 SNPs and we fit the maximum likelihood estimator, also we'll fit any phenotype such that there's 0 noise, which is pretty unrealistic. So that's kind of the basis functions are very nice because they allow me to kind of plot these things and visualize these things. But I cannot plot 1,000,000 SNPs, but it's kind of the equivalent there. And if we look at the regression coefficients, then we'll also observe that, well, if we increase the number of these polynomials, then we get regression coefficients that have a huge magnitude here. So what this tells us that the variance or the variability in our regression coefficients grows dramatically with the order for the maximum likelihood estimate. Well, so this kind of gives us the idea of what is generalization performance. So let's say, I mean, this is our error. I mean, this is just a squared error as before, where we have the average. Oh no, it's the sum over the squared error for each y times 1/2. We can go from there to the root mean squared error, which is independent, in order to make it independent of the sample size. I mean, this grows linear in the sample size, this one doesn't. So we just take 2 times the squared error here, divided by n, and take the square root of it. And well, we can measure it on the training data. This is what we've done before, which for the 9th order polynomial is 0. But we can also use it to measure on test data that has not been used for training. So training is kind of the data that we use to estimate the parameters, and might have some other other data, for example, new data that comes in, or some data, as you said, in a cross-validation procedure or so, that you hold out in order to see, okay, if I fit the model on my training data, does it make sense on my test data? And then we see that basically, if you plot the root mean squared error we can measure it on the training data and on the test data, then typically on the training data it's smaller, so we get a better fit typically on the training data than on the test data. So that is kind of like the difference between these two curves is basically the amount of overfitting that you have for a given model. And we observe that both of these, well, increasing the polynomial goes down, and at some point they diverge, where we get perfect prediction on the training data, but if we go on the test data with these these huge regression weights we get, and these super curvy functions, our predictions become really, really bad. So it basically means that we can measure both overfitting and underfitting using test data. And a model that gives us a good test data performance is probably a good model. So what we already observed is that the number of that the order of the polynomial is crucial for over and underfitting. So if you have a given data set and we increase the complexity of the model, we first get better fitting when we increase the model at some point, because it reduces underfitting, and at some point the model becomes too complex and we get overfitting. But also the size of the training data is crucial in order to get an accurate model. For example, if you start, let's keep the polynomial at 9 now, and we start with 10 data points as before, then we get the same function as before. Now we go to 15 data points, and we already see that a lot of this wiggle that we had before goes away. And well, once we have 100 training data point, then actually this 9th order polynomial gives us a quite accurate fit of our original true function. So what this tells us is that, well, if you have a complicated model, you can fit it if you have enough data. And but on small, so now we have already identified 2 things that influence overfitting and underfitting. It's the number of training data points, it's the complexity of the models, and these 2 things have to be traded off. And the other observation is that probably if we had used the 3rd order polynomial, which got probably the best fit for 10 data points, we now probably have a model, because it has a lot of free parameters that we can adjust to the data, gets a much better fit, much more realistic fit of the true function than the 3rd order polynomial would have done. Okay, so the question is now, how can we trade off these kind of overfitting and underfitting things? And what we have seen before is the application for that in order to choose the kind of a polynomial, how to adjust the degree of the polynomial, how to fit the parameters there. Or the other example that we've brought is just a high-dimensional regression where we, for example, have many mutations, many SNPs, and we want to predict the phenotype. Note, when we fit a single binary variable, then the linear model is actually the most general. So whatever basis function we create for a single binary variable, the binary model, I mean, it cannot get more complex. You can still only get, if you put a binary variable through basis function, it will still be a lot of binary variables. Okay, so, and the way to avoid overfitting is what we call regularization. Right? It's again kind of penalization, for which the most common version is the so-called rich regression. And, well, solutions to avoid overfitting. We've already seen. Intelligently choose the number of parameters, a way to avoid overfitting, because the number of parameters in the model, so the number of regression weights that we fit to individual basis functions, influence the complexity of the model. A model that is too complex overfits, a model that is has too little complex underfits. Get more data also helps you to reduce overfitting. And the other one is to use regularization. And well, rich regression basically corresponds to using a quadratic regularization, where we just, instead of using for our error just the squared error before, the sum of squares on the training data, now we add an additional term which depends on this parameter lambda here, which measures the sum of squares of the regression coefficients. So this is, if you write it as a sum, this is just sum over beta I square. All right, and for example, if you fit this to the same model as before, where we got these values of minus 100,000 or so, these would give a very high penalty. So there's kind of now a trade-off between getting a perfect fit and still not making the regression coefficients too large. Now, if we compare different lambda values, this is basically lambda equals 0 as before. Now, if we set log of lambda to minus 18, we get something like that. Each of those keeping the 9 basis functions the same. If we set log lambda to 0, we get something like that. So choosing this parameter lambda right also is really important. And it's a way to control over and underfitting while keeping the rest of the model the same. And well, if you look at again at the regression coefficients over different lambda values, then you see this is basically setting lambda to 0. This is what we've seen before, these huge values. And if we set it to some reasonable value, then we get whatever regression coefficients might be good. But if we set it too large, then all the regression coefficients go to 0. So getting this parameter right is important. And now we can again plot the training and test error as a function of lambda, where basically here we have the case where, so this is log lambda, so this is very small values of lambda, where we get a perfect prediction of the training set, because we have this function that perfectly fits the data, but it predicts very badly. Then if we go in this direction, we reduce overfitting, and then we have this region where basically training and test track each other very well, and at some point we get underfitting because the regression weights all go to 0. And well, basically for a function f, it kind of tells us there's now a trade-off, right? I mean, there's we said if the regression values if the regression values can wiggle a lot, then this probably means that there's a high variance. But it also means that if we observe enough data, we fit the true function very well. And for that, we basically introduced the concept of bias and variance of a function estimate. Basically, bias is the expectation of the difference between the true function and our estimate, where the expectation is over the true distribution of the data, which is unknown. And variance is now the expectation of the difference between the estimated function and the expectation, so the mean estimated function, and the squared difference of these. So there's some braces missing here, right? And well, let's do an experiment to get an idea what bias and variance mean. So I create 100 random data sets with a number of each of those have 25 samples, and now I use 25 of these radial basis functions and use different lambdas. So if I now have one lambda value which is pretty large, so log of that is 2.6, then I get functions that are all pretty close together. So where the variance in the function is pretty small. But if I look at the mean, then the mean basically is very close to 0, and the difference between the mean and the true function gets pretty large. So what this means is that basically this difference between these means here gives us an estimate of the bias. So it's a difference, the expected difference between the estimates and the true, which is basically because the true function is fixed. You can basically take the average only over the estimates. So it's the difference between the average in the estimates and the true functions. And here, this is basically, if we now subtracted this average here from those, then we get the variance. Yeah.
So the one on the right, that would basically be no bias, but
no, this.
No, is it point by point?
Now here, no, it's the expectation. So it's.
So it's across all xi's.
Yes, it's across xi's. You would integrate over xi basically, and. So here we basically observe that here for this large lambda value we have quite a bit of bias, because the difference between the true functions is and the average is large. So it's basically bias of the estimate towards 0 and very small variance. While if we increase the lambda, then decrease the lambda, then we get less bias, but larger variance. And if we still decrease the lambda, then we get even less bias. We get 0 bias at some point, but the variance goes up. And well, the limit of this, basically, the observation is basically that, well, bias decreases with smaller lambda, or it increases with larger lambda, and the variance increases with smaller lambda, or decreases with larger lambda. Yeah?
So really the bias estimate, that's the expected value of the absolute value of one function minus the other?
The biased estimate is the bias. I mean, what we're usually interested in is the absolute bias or so. I mean, it's, if you want to put it into a number, or the squared bias or so. But bias is basically the difference in the expectations. And the limit of this is basically the 0 biased estimate is the maximum likelihood estimate, which has lambda equal to 0. But it has a very large variance. That's basically if we fit this 9th order polynomial with maximum likelihood, we have 0 bias. So 0 bias if the true function is in the basically in the considered model. So the true model has actually to be fittable, but variance increases. So by introducing regularization, basically this lambda is a regularization parameter. By introducing regularization, we introduce bias, but we reduce the variance. So it's kind of, and in reality there's a trade-off between these two. There's what we call the bias variance trade-off. So, and this basically, so if the model, as I said, is a true function plus noise, then the mean squared error, which is the kind of can be seen as the expectation of the squared difference of the estimate and the y value, so basically of the true value, and this can be written as the square of the bias, because while we're taking an expectation, then basically bias. I mean, the best that we could do is plug in the true function here, in which case we had 0 variance because the true function is fixed, and 0 bias, right? So, and the only thing that would introduce anything here in the mean squared error is noise. But by doing an estimation, our estimate has bias and variance, and the bias basically in this mean squared error appears as a squared, and the variance like that.
That's maybe just plugging in, like adding f true and subtracting f true from that interior thing.
Right. Yeah. If we plugged in f true here instead of f, basically if f true was our estimate, then bias would be 0, variance would be 0, and the squared error would only be noise. And in order to achieve the smallest mean squared error in expectation, we basically have to, I mean, noise we cannot influence. Noise is just inherent in the data. But we basically have to reduce the sum of the bias squared and the variance. So in order to get an empirical idea of this, let's again use these 100 random data sets and learn the same same model consisting of 25 RBFs for different lambdas. But additionally, well, again, compute sample estimates of bias and variance, which is just because we know the true function, we can compute the bias, and we can compute the variance, of course. The problem is bias. So if you don't know the true function, you cannot compute the bias. You can always compute the variance, because the variance, yeah, it's clear. But here, because it's synthetic, we can compute the bias. Now additionally, we also generate 1,000 test data points in order to get a pretty good estimate of this expected mean squared error. So these 1,000 data points are not used to train, which tells us what the mean squared error should look like. Now if we plot basically bias squared, the variance, and bias squared plus the variance against the test error, then what we observe for different lambda values. So from here to there, we increase the lambda, so we reduce the variance but increase the bias. Then we see that this intuition holds, that basically the point where the sum of bias square and variance is the smallest, also the mean squared error is the smallest. And the difference between these two curves is noise. It's a constant, basically, right? So something, I mean, that is kind of one important thing. An unbiased estimate is not always the best estimate. If you can get a biased estimate which has much smaller variance, then often this is good. And you ideally want to trade these things off with each other.
So would you choose a lambda that has the smallest mean squared error then, those Chris in the curve?
Yeah, I mean, the problem with this curve is that now what we had to do in order to get this curve is, well, I mean, the problem is we cannot measure the bias, right? Because we don't have the true function. But what we can measure is this. And we know that the minimum, or we can measure it by just holding out parts of our data and not use it to train, right? And measure basically the mean squared error on that part of the data. The problem with this procedure is, of course, quite wasteful because, well, if you don't use that part of the data, you won't get an as good fit because your sample size becomes smaller. So it's pretty hard to do this trade-off. The question is, how can we do it well in practice? And that is something that we'll discuss in a bit. Okay, so, well, regularization. So far, we said, okay, our error in ridge regression is a squared error, and this regularizer where we have this lambda and basically q equals to 2 because we have to kind of if we take the absolute value of sum of absolute values of each beta weight to the power of 2, that gives us the ridge regression. But we, in principle, can choose any kind of regularizer. Right? The typical regularizers, a large group of regularizers, can be explained exactly like that, where you have written down exactly like that. We take the absolute value and you take it to a power. And well, the ridge regression corresponds basically to this. I mean, what this is basically, this is a coordinate system where in the middle we have so it's plotted two weights. So beta is two-dimensional here. And now these are kind of the contours of this regularizer. So basically, whenever we are here on this circle, we get the same squared penalty, right? Now, if we take q equals 1, for example, then we are on this diamond here. Or if we raise the power larger than 2, we get something that goes towards a square. So the infinite norm, basically, if q would be an infinity, then then the penalty would be a perfect square. And if we take a penalty that is smaller than 1, we get something that is actually a little bit, how do you call it? It's non-convex. So, and the interesting thing is that the models that we get, if we decrease the number, or basically this exponent here, we'll get the solutions get more and more sparse. So because the optimal parameters, basically, if you observe here that if you go, for example, to this 0.5, then the penalty, in order to get the same penalty with both beta 1 and beta 2 unequal to 0, you can introduce much smaller beta values than if you set one of them to 0. So this gives a large incentive to, if you want a large value in one of them, to set the other one to 0. So there's sparsity in this direction, and the most typical models of this are basically if q equals 1, you got the lasso regression, and this is the ridge regression, the quadratic one that we used before. Some issues, well, you want to find the solutions of these. The way we did it so far was by taking the derivative or the gradient and then set the gradient to 0. You can, which for the quadratic we can do it analytically. The problem is, I mean, in general, it doesn't have to be analytically, and we might use some sort of gradient optimizer techniques. Yeah? The problem is when we use something that has edges here, then this function here becomes non-differentiable. But as long as this q is larger than 1, we can still find an optimum. There are basically, which just means that we have to be a little bit tricky and to use some specialized optimizers. it gets problematic when Q becomes smaller than 1. So if you want really, really sparse solutions, then the problem is that the functions become non-convex. And for cases where the function is non-convex, there is no easy way to find the global optimum. Basically, to find the best model that minimizes the sum of the squared error and this regularizer. And I mean, if we can still optimize it, but if we find an optimum, it doesn't need to be the global optimum. It's impossible to show that it's the global optimum for most cases. Well, how can the sparsity be explained? So, say we have the usual rich regression model. Then we have something. We have the sum of a squared error. So basically, our data. So we have two beta weights, and by basically the best squared error. So the squared error is kind of increases in circles. The smallest squared error is what our maximum likelihood estimate gives us, right? This is here. Now, we also have this penalizer here, which basically wants, I mean, if we just want to minimize, if we only want to minimize the squared error, we would go here. We would set beta 1 to this value and beta 2 to this value. If we want to minimize the penalizer, we would go to the origin. But we trade off these two. The way we trade off these two is by ways of lambda, but the point where they meet is here. So the optimum rich regression estimate is basically the point where some of these contour lines of the penalty and the squared error meet. Now, if we set the penalty to be the lasso, to the sum of the absolute values, then we get this diamond here. And this kind of gives an idea why, if we use this diamond, why it enforces sparse solutions, or it doesn't enforce, it encourages sparse solutions, because many of these optima now fall because of this shape here will fall on one of the axis lines. So here in this case, the optimal solution of the sum of the penalizer and the squared error would set beta 1 to 0. And for that reason, we get a sparse solution. Note also that, I mean, if you think of lasso as being non-differentiable, I mean, it's only non-differentiable at points where we actually touch one of the axis lines. You can say, oh yeah, I mean that's just, I mean, measure 0, right? I mean, the problem is, because of this property, these measure 0 places where the lasso is actually non-differentiable are usually the solutions. So this is what makes it really, really hard to optimize. Yeah, so this is the last slide before I finish for today. So, well, I mean, can get even more general. So in general, basically, so far we talked about squared losses and some absolute value to some power. But in general, basically, we can plug in any kind of loss function that depends on the data and the regularizer. And, well, many machine learning methods can be expressed within this framework. For example, linear regression or rich regression is a squared loss and a squared regularizer. And the support vector machine even can also be interpreted as such a linear model, where we have a linear model with a hinge loss and also a squared regularizer on the weights. Or the lasso would correspond to a squared loss and one regularizer. And the list goes on like that. You can explain boosting like that, many, many models. Doesn't mean that it's the best way to optimize these models, but it's an interesting insight and interpretation. And well, if I want to optimize a boosting or a support vector machine, I can basically write it down as kind of a loss function, a regularizer, and just minimize the parameters of that. Well, the question is how to determine the best suitable loss function. For example, if we just restrict ourselves to penalty with Q and a squared error, and this is something that we'll discuss next time, which is model comparison. Okay.